In the earlier videos, we learned how to formulate LPP, that is to formulate constraints and objective function. Now we are going to extend this problem to find out the actual real values, right? For example, if you have to maximize the profit or minimize the cost, then we will have to arrive at that value, that cost value or the profit value, and using a graphical method technique. So we'll have to plot a graph, we'll have to find the feasible region, feasible solution, optimal solution. It can be either to minimize cost or maximize profit. So there are multiple steps here. Let's go step by step. You will have to first get the objective function, get the constraints, and then get all the possible solutions in which the cost can be optimized. And then those values need to be plotted in the graph. And from there, we'll get a feasible region and an optimal solution. So let's take an example to start with. Now in this example, there is a new cereal that is being formed by Kellogg using a mixture of bran and rice, right? And there is a minimum requirement of proteins and iron in this mixture. They have given the minimum requirement, right? And rice contains certain amount of protein and iron, and bran contains certain amount of protein and iron. Now using this constraints and all these variables, we'll have to find out the minimum cost that can be incurred on arriving at this new cereal, right? So it is also mentioned that minimum cost for producing this new cereal is 5 rupees per kg for bran and 4 rupees per kg for rice. So using this, we can arrive at objective function. Now let's first assume that there are X units of bran and Y units of rice. So it's given that cost for 1 kg of bran is 5 rupees and cost price for 1 kg of rice is 4 rupees. So bran is assumed as X units for bran. So it is 5 rupees per kg of bran, and cost price for rice, which is Y, is 4 rupees per kg. So the total cost would be 5 into X, and here it will be 4 into Y. This is for rice and this is for bran. So the objective function is 5x plus 4y. Now let's arrive at constraints. So what are the main two things that we are trying to minimize cost with? One is bran and one is rice. And what are the other variables? The other variables are protein and iron. So how much of protein is there in 1 kg of bran? So we have 80 grams of protein and 40 mg of iron. And for rice, there is 100 grams of protein and 30 mg of iron. Now this 80 grams is per kg, right? So what will happen for X units of bran? It's going to be 80 into X. So this is going to be 40 into X. This is going to be rice. So rice is Y. So 100 into Y and 30 into Y. Now adding this, we'll get our constraints. So our constraints are 80X plus 100Y. Now there has to be some limit here. The limit is at least 88 grams of protein and 36 mg of iron should be there. At least. That means it can be more than 88 grams also. So it can be greater than or equal to 88 grams. This is our constraint number 1. What is constraint number 2? Constraint number 2 is 40x, we add this, plus 30y. Again, this should be greater than or equal to 36 mg. So this has to be greater than or equal to 36 because minimum of 36 mg of iron is required per kg. So this is our constraint number 2. And also X should be greater than or equal to 0, Y should be greater than or equal to 0 because they cannot be negative quantities of bran and rice. So we have our constraints here. We've got the objective function and the constraints. Now the next step is to plot the graph. To plot the graph, we need the points. And how are we going to get these points? We're going to assume X and Y values in both of these constraints and arrive at points. Let's take the first constraint, which is 80x plus 100y. So instead of greater than or equal to, we are going to make it as equal to. Assume that it's equal to 88. And then we are going to get the values of x and y. So to start with, we'll assume x is equal to 0. If x is substituted in this as 0, we will get 100y is equal to 88, which means y is equal to 88 by 100, which is y is equal to 0.88, approximately 0.9. So our first point is 0 and 0.9. So we've got a first point. Now let's try to get the second point. To get the second point, we'll assume y is equal to 0. If you put y is equal to 0, what's going to happen? You'll get 80x plus y is 0, so it will be 0 is equal to 88. So x is equal to 88 by 80, that is 11 by 10, and that is 1.0. So we've got our second point, which is 1 and x value is 1 and y is 0. So 2 points are here. Now let's do the same thing with the second constraint. Second constraint, 40x plus 30y equal to 36. So we'll substitute x as 0. So we'll get 1.2. Now we'll put y is equal to 0 here. So we'll get x is equal to 0.9. So we've got our 2 more points, which is 0 and 1.2 here. And in this case it is x is 0.9 when y is 0. Let's call this as point A, point B, point C, and point D. Points are A is 0 and 0.88 or 0.9 approximately. Point number B was 1.1 and 0. Point number C, this is for the first constraint, which is 80x plus 100y greater than or equal to 88. Point number C is 0, 1.2, and D is 0.9 and 0. This is for second constraint. So let's plot the graph now. I have taken a scale of 2 centimeter. So 2 centimeter is equal to 0.1. So let's take the first constraint, 80x plus 100y. So what are the points? First, let's take the point A, 0 and 0.88. So x is 0 and y is 0.88, somewhere close to 0. So this is our point A. And the second point B is 1.1 on the x-axis, this one, and y is 0. So this is our second point. Let's join these points. Okay. So we have our first constraint, which is 80x plus 100y. Now let's take the second set of points C and D. C is 0. For C, we have 0 and 1.2. 0 and 1.2. So it's here. So this is our point C. Point D is 0.9 and 0. So it's here. 0.9 and y-axis is 0. So this is our point D. So let's join C and D. So this is our constraint, 40x plus 30y. Now what we'll have to do as a next step is we'll have to arrive at feasible region, for which we'll have to shade. Now since it is greater than or equal to, we'll always have to shade outwards, that is away from the origin. The shading will be like this. Right, let's take this one. The shading will be in this direction. So this entire region will be shaded. Similarly, for the second constraint also, it's greater than or equal to. So even for the second constraint, we will shade it. Right? So let's shade it like this. Now let's shade for the second constraint. We'll start on this line. So when you look at the shading portion, right, you'll have to choose the portion which is overlapping between both the constraints. Now if you notice, this is the region that is overlapping. So this is called the feasible region. Now we'll have to figure out the corner points. What are the corner points? So first corner point is C, because the shaded region starts from here, C. Next one is B, because this is where it overlaps, right? So C, B, and then we'll have to take the intersecting point where these two constraints meet. It meets here. So from the graph, we'll have to figure out what that point is. Somewhere close to 0.6 and somewhere close to 0.4. So C, B, and E. I think E is 0.6 and 0.4. It's the other way around. x-axis is 0.4 and y is 0.6. So corner points are 1.1 and 0, which is our B, and C, which is 0 and 1.2, and E, which is 0.6 and 0.4. Now, what do we have to do as a next step? We'll have to substitute these points in the objective function. When you substitute, you're going to get the actual values of cost. That's what we're going to determine, right? Determining the cost. So we're going to get the cost when we substitute these values in the objective function. So let's substitute. Let's take the objective function. Z is equal to 5x plus 4y. Let's substitute point 1.1 and 0. Substitute 1.1 and 0. So this is our x and this is y. So what do we get? Z is equal to 5 into 1.1 plus 4 into y. Y is 0. So we get 5.5. Now we will take the second corner point, which is 0 and 1.2. We'll substitute 0 and 1.2. We'll get z is equal to 5 into x, x is 0, plus 4y, 4 into 1.2, which is 4.8. Now let's take the third corner point, which is 0.6 and 0.4. Substituting this in objective function, we get z is equal to 5x. X is 0.6 plus 4 into y, which is 0.4. We'll get 3 plus 1.6, which is 4.6. Now we have three values here: 5.5, 4.8 and 4.6. So these are the feasible solutions, right? So by substituting the corner points, we get feasible solutions. And since we have to minimize the cost, we will take the minimum of these values. What is the minimum or the least? Least is 4.6. So this becomes our optimal solution. So optimal solution is when z is equal to 4.6, and it occurs at what values of x and y? 0.6 and 0.4. So to summarize, when we have to find the value or the minimum cost for a linear programming problem, we first have to obtain the objective function, get the constraints, then assume x is 0 and y is 0 and get the points for both of these constraints. So 2 points for this constraint, 2 points for this constraint. Plot them in the graph, find the intersecting point. Since it is greater than or equal to, it will be outbound, away from the origin. Shade the region and take the overlapping region. Get the corner points. Once you get the corner points, substitute those points in the objective function. Take the minimum of those values. That will be the optimal solution. And all of these z values are feasible solutions.